So finishing our notes from last week, we were talking about linear functions. So just want to review the different ways that we can talk about linear functions. So the point of view, right, or the perspective that we're looking at is if we're verbally talking about a linear function, then we might say that it's a polynomial and it has degree 1. If now we're looking at the algebraic perspective, then we might write it in function notation using a linear representation like a y equals mx plus b, or maybe even something in standard form like this, ax plus by equals c, noting that both of these show us that x is to the first power. If our perspective is a graphic perspective for a linear function, then we expect to see a straight line. We talked about how that line could be vertical, how it could be horizontal, or how it could be a slant or oblique line. And when we graph it, then we often talk about things like what is the slope or the rate of change in this, or we might say things like what is the y-intercept, right? So that's the value of y when x is 0. And lastly, if we're doing an analytical perspective, we would say that this is a non-zero function. It has a constant rate of change. It has an initial value. Of, let's say, 0b, and that might be the same thing as saying when when x is 0, f of 0 equals b. Right? So this is my equation graphed over here. Right? Here's my y-intercept right here, 0b. We can talk about the rate of change, right? The delta y over delta x, and how that's a constant which we represent as slope. Okay, so we've spent a lot of time talking about linear functions, and the big thing that we want to do now is we want to look at modeling, because remember our growth here is not just to understand linear functions, but to actually use them to solve problems, to apply what we know about linear functions to real problems. So I'm going to show you what some mathematical modeling would look like. This is a lot of the work that we do actually in statistics. We studied two different variables, right? And we would say, are they associated, right? Does one change as the other one changes? So we're saying that they vary in tandem, right, in some way, but we haven't really decided what that way is. But basically is the independent variable, right? Usually the independent is our x value, and the dependent variable, right, that's our y value. How are those guys related to each other? So one of the first things that we usually do when we're trying to make a decision like this with real data is we create a scatter plot. And our scatter plot should be our first indication of whether or not our data is in fact linear, because it should show us that our points, by and large, sort of line up, right? The dots where the independent and dependent variables correlate, they should go in a straight line. So this is definitely a linear graph, this first one. We would even say that this is like a strong linear relationship. And then we've got this next one. I would say that this still kind of is linear. It still kind of makes a line, but it's not really very tightly into a line, and so I would say that this is weakly linear. Now, this next blob over here is a little amorphous. I would definitely not characterize these dots as falling into any kind of line shape. I would say that these have no correlation. I don't see any predictable pattern where as x changes, y changes in a way that I can really predict it. And lastly, these ones, this is definitely not linear. To me, this looks quadratic. And it actually looks like it's got a pretty strong association where the x values predict the y values in a way that makes me think of negative x squared. However, we want to be really careful because the word correlation is always used to describe linear. So write this down. Correlation is for linear and nothing else. So even though up here we noted that this looked like a parabola, instead of calling it quadratic correlation, we'd call it a quadratic association. We would not call it correlation. So this word right here is very, very, very specifically tied to things that are linear. Correlation and linear go together. All right, so now that we have our dots plotted on a scatter plot, we want to look at this and have some sort of measure, right? So it's not really good enough just to look at it and say, well, I think these are really tightly aligned, or I don't think these are really tightly aligned. Knowing mathematicians, right, we want to have a numeric value or calculation that we can use that's going to help us figure out what that association might be, right, or what that correlation might be. So that's where the correlation coefficient R comes in. Okay, it's basically a number. The smallest value is -1 and the largest value is +1. So it's always a value between -1 and +1. And it's telling us the strength and the direction of linear correlation. So basically, if you're right here in the middle and you're at 0, that's no correlation. Okay. And then as the number gets closer and closer to -1, it gets stronger and stronger and stronger. So you could have a -1, which would be a perfect negative linear correlation. That means that all of your dots are just perfectly on a line together. Okay. And then on the other side, moving away from 0 in the positive direction, right, the correlation's getting stronger and stronger and stronger until finally, if we had an R value of +1, we would say that we have a perfect correlation, but this time in the positive direction. So when I look at my scatter plot, all my dots are lining up absolutely perfectly on a line, but just with a positive slope. So our R correlation coefficient is both describing the strength, right? That's as we move from 1 or -1, and the direction, is it positive or negatively associated for any linear correlation. Then we have something known as the coefficient of determination. This is literally R squared. Sometimes you see it as capital R, and it's measuring the percent of data, that's our output data or our Y values, that can be explained by the linear model that we come up with. So where is this linear model going to come up with it? Right? Well, what we're going to do is we're going to use the calculator to find this equation for us, known as the line of best fit. In other words, can I get the graphing utility that I have, right, or a statistical app or tool to help me find a line that can pass through my scatter plot and be the best possible line at showing me the relationship between all the different points that I have. Okay, so let's look at this first example. Can you match each graph with its probable R value? So one of the first things to note is that this one should have a negative R value because it's got negative slope. This one over here should probably have a positive R value because it's got positive slope, right? They both look relatively moderate. I wouldn't say really strong, but the dots are all pretty close together in a line. So I would say that this guy right here is probably positive 0.76. It's positive, it's kind of close to 1, it's not super close. Right, and then I would do the same thing on the other side, honestly. It looks like this guy over here. It's pretty strong, right? But it's negative. So I would say that this is probably R equals negative 0.74. So again, kind of getting close to -1, so it's pretty strong. So look what I'm left with. I'm left with r equals 0.22. See this guy? That's actually really close to 0, which means that should be associated with something that kind of looks a little bit like a blob. Well, honestly, my last two choices, they both look a little bit like a blob. To me, this one's a little blobbier. You see that when you outline it? Whereas this one has at least a little bit of a this going for it, even if I have to kind of do this to make all the points fall together. So that makes me think that this is probably r equals 0.22. I would say that this blob looks a little bit, oh, kind of looks like a little Halloween ghost. He looks a little bit more positive than he looks negative, right? And then this one for sure has a negative slope or relationship to it. This is probably r equals -0.49. Okay, so that's r, right? When we're matching up r, our correlation coefficient to a scatter plot. All right, so let's take a look at this example. A researcher is studying the relationship between newborn weight and height. After making a scatter plot of 50 data points, she calculates the line of best fit to be, and we call this y hat. That's the line of best fit or the prediction line. (0.45t plus 7.125) and the correlation coefficient r at 0.853. Find and interpret the value of r. Oh, well, I guess I didn't have to find it. I just have to interpret, right? So r equals 0.853. So first of all, I notice that r is positive, right? That means that as the newborn's weight increases, their length is also going to increase, right? A change in tandem, it's a positive slope, right? So my line probably looks something like this, which means as this one's going up, this one's going up, right? As the weight increases, the length increases, or as the length increases, the weight increases. The other thing that I know, because this value is pretty close to 1, right, is that this is a strong linear correlation. In other words, these two things are pretty strongly tied together. One is probably a pretty decent predictor of the other one. And that should make sense to you, right? If you have a really long baby, they're probably going to weigh more than a really short baby. Okay. You guys are going to be doing a problem on your calculator just like this one. I'm going to give you some data and I'm going to ask you to plot this data in your calculator and use your calculator to find a linear model that we can use to make a prediction. In this case, my independent variable is the price per box, so that's going to be my x, and my dependent variable is going to be my demand or my boxes sold. So if I were to put all of these in my NumWorks calculator, and then I would make a scatter plot of these. So basically what my scatter plot is going to look like is there's going to be a bunch of dots that are going to kind of show up as I'm plotting each one of these ordered pairs. Remember, we're putting the price per box down here on the x-axis, and on the y-axis we're putting the demand. And it looks like as the price per box increases, the demand is falling. So this might be like 40K up here, and then maybe like 20K down here. So when you make your scatter plots, I want you to make sure that you label and scale your axes. So I create my scatter plot. I notice that my dots kind of look like this. It definitely reads linear to me, and it definitely reads with a negative slope. So now I would go into my NumWorks calculator and I would find the equation for the regression line. So again, once you put this data in NumWorks, this is going to be in your X1 column, and this is going to be in your Y1 column, and you make your scatter plot. If you press OK and then select regression, it should come up with an equation for you. You should find that this equation is y equals -15,000 359x plus 73,622. And now I want you guys to be able to interpret the slope and the y-intercept of these. In this case, the slope is here, right? For each increase in price per box, that's supposed to say box, the demand falls 15,359. Right? That's what we should be noticing. That's showing us the rate at which x and y change in tandem. Find the value of r and r squared. And again, these values are going to come up in your NumWorks calculator for you. Your r value is negative 0.98. So we should notice that this is negative, and that's going to match our slope, right? We knew that that was going to be negative because we have a negative relationship between x and y. It's also very close to 1. So I would, or negative 1. So I would say that this is a very strong linear relationship between the price per box and the demand of boxes sold. In other words, as x goes up, y goes down. And then the r squared value is 0.96. The way we want to interpret this is that 96% of the output, and again our output was our demand, can be explained or predicted by our equation. By the line of best fit. Okay. So the last thing that we want to do is since this is a really, really good linear model, right? It's very close to 1 or negative 1, which means it's very strongly linearly correlated, and our r squared value is very close to 100%. We should be able to use our y equation to make predictions. It says predict the weekly demand if the company drops their prices to $2 per box. So what I'm going to do is I'm going to plug in my x value at $2 a box, and I'm going to see if I can predict what the demand will be. So if the company drops their price to $2 per box, the demand is going to go up to 42,904 boxes, right? And what we should notice, right, is exactly what we saw the whole time through, and that is that as the price goes down, the demand goes up.